Yesterday we found that equivalent resistance, and I want to use that word like we used it for capacitance. Equivalent resistance for resistors in series is just the sum, the simple sum. And we did that for series. And of course, if you are looking on your equation sheet, it's on the equation sheet, just something like this. So it's for any number of resistors, you just add the sum. You can probably imagine what parallel is going to be. It's not gonna be a huge leap, but we should probably do the math necessary to take a look at it. So I'm of a mind that I shouldn't have to do this, that you should be able to do the steps necessary to prove that the sum, the equivalent resistance for resistors in parallel is going to be the sum of the inverses, because you guys have done this already. We did it with the capacitors, but I think it probably is still in my best interest to have spent at least a little bit of time going through showing you how we can prove it. Remember, Kirchhoff's laws can be used to do any of the problems that we do with capacitors and any of the problems we do with resistors. It just represents the hardest way to do it. So we'll use Kirchhoff's laws to find a relationship for parallel, just like we did series. And then we'll probably use stepwise reduction to analyze most of our circuits. But this week, you're going to get to see what it means to analyze a circuit using Kirchhoff's laws. And I hope you understand that you'll appreciate why it's nicer when you can use stepwise reduction. So let's do a quick Kirchhoff's couple of loops here. Do you see that there's 3 possible loops through this circuit? I'm going to look at 2, but there's a third loop through here. It's just that one is probably less useful to us. It's not a problem, but it's just not going to be as much use. So I'm going to look at this as loop 1, and this one is loop 2. Generate 2 relationships. It's not hard. I'm going to have V minus V1 equals 0. That's the Kirchhoff's rule through loop 1. You guys see that okay? And then V minus V2 equals 0. That's loop 2, but we have something different this time. We have a junction right here and a junction right here. Current into a junction has to equal current out. This is Kirchhoff's second rule. So there's a current going in here. I'm going to say this is I total, because this would be the current that passes through the battery. But that there's a split, and I1 goes on the side with R1, and I2 goes on the side with resistor 2. Now, Kirchhoff's second law says that I total has to equal I1 plus I2. So this is using Kirchhoff's laws to come up with relationships that could be used to solve the circuit. This could do it. Now, this part I think is going to be pretty straightforward. We did this yesterday. I think we can all say V is going to have to equal V1, but we know that V equals IR, right, from yesterday? Does that look familiar to you? So V1 equals I1R1, and V2 equals I2R2. That all good? Well, V equals V1 and V equals V2. That has to be true as well, right? All right. Well, let's do this. I total equals I1, but I1 is V1 over R1. Plus I2, which is V2 over R2. All good? But V1 is just V, and V2 is just V. Still all good? Any question about that? Does it make sense then that V total, or just V, equals I total times whatever the equivalent resistance is, not GQ? Wouldn't that have to be true, that the total current provided by the battery is based on the equivalent resistance that the battery sees, so that I could write I total as V over R equivalent. Does that all make sense? So can I bring all these together and get that V over R equivalent equals V over R1 plus V over R2? And there it's proven in a parallel circuit. The resistance goes through the inverses to get the equivalence. The exact opposite of capacitors, right? Capacitors in parallel, you just add them all together. Resistors in parallel, we have to do the inverses. You understand that? You see it? Recognize it. Be prepared for it. This also suggests something that I don't know if you see. Resistors in parallel have less total resistance than the individual resistors. We had the same issue with capacitors in series. Resistors in parallel, though, less total resistance. Think it through a little bit. Less total resistance with the same voltage supply means more current, right? In fact, if I write it like this, current equals voltage divided by resistance. So if the resistance gets smaller and I don't change the voltage supply, then I must be drawing more current from the battery. Does that all make sense? Well, if you look closely here, why does that happen? What do you think is happening here? Yes, sir?
You're forcing less charges through like a smaller space, so it's easier for them to flow.
Yeah, that's exactly it. More lanes of travel, like for cars, right? We say that current takes the path of least resistance. But if you add more pathways, you can pass more current. And that's what we've really done here. We're allowing more pathways for the current to pass through. I know you're thinking, well, this pathway hasn't changed. But remember, that offers zero resistance to the charges. So when we start having actual resistors in play, and you're pushing those charges through the resistors, offering them more places to go accommodates the flow of more charges. And that's why this whole system works the way it does. And of course, that kind of a verbal description lends more credence to why Kirchhoff's rules are so powerful. Now, ultimately, proving this is not super important. Being able to use it is what's important. I don't think we have to do a purely parallel circuit. I think you guys probably can handle something more complicated. So let's do a complex circuit. But this time, I don't have to play with the kid gloves on. I can start giving you stuff that's going to be maybe not so mathematically pleasing to you guys. I'd like you to solve the circuit. Solving a circuit has three major things you should be able to do. You should be able to calculate the power, current, bless you, and voltage for any resistor in the circuit. And just as a reminder, power, voltage times current, current squared times resistance, voltage squared divided by resistance. I want to make sure for anybody who wasn't paying complete attention yesterday that we have all of those. And of course, voltage equals current times resistance. And I can't write this down because I don't want to, but resistors in series, do they have the same current or the same voltage? We made this decision yesterday. Resistors in series have the same current, just like capacitors in series have the same charge. So resistors in parallel, they must have the same what? Voltage, just like capacitors in parallel. All right. Stepwise reduction. I see a roadmap here. Something that reduces the 150 into 300. Look like a right kind of path for you guys? I'm gonna stop there. I want you to do the rest. I think you can. All right, so I don't really feel like I have to do all the fractions and everything. I feel like you guys can handle the math here is pretty straightforward. But you do have to make sure the application that you do is right. So when you get here and you find that it's 1/4 of an amp, when you go back a step, should I apply voltage to both of those or should I apply current to both of those? Current. Resistors in series must have the same current passing through them. So for all of you who just had voltage, change your notes. Put it in there. Or don't, because you never look at them anyways. But if I'm going to take the time to do it, when you step back to series, series has the same current. So 1/4 of an amp here, 1/4 of an amp here. That means 25 volts and 25 volts. Questions about that? All right. When you step back here, one of these is done. This one's 1/4 amp, 25 volts. But we have a system that is in parallel, so parallel gets the same voltage. So you get 1/6 amp here and 1/12 of an amp there. Does this make reasonable sense? That phrase, current takes the path of least resistance. Do you see it there? The resistor that is the smaller value has more of the current, and the resistor of larger value has less. Now, you can't see this other thing I need you to see here. So I want to try something else real quick that's, I think, easy, but I need you to do it. I need you to see it. Can you find the voltage across the circuit elements for each case? I want you to see something. It was not intended to be hard. Your reduced circuit here, what do you get for your equivalent capacitance? Migo's trying to do it in his head. Was he successful? What do I have to do to get this answer? What do I have to do to find the equivalent capacitance? I know. What do I have to do that? No. You would do that if it was a resistor. This will be 300, sure. But you don't do that with the capacitor. And thank you. 200 over 3. All right. So no problems there? You need the charge here. You need the current here. So Q equals CV. All right. So you get the charge, which is 600, 200, so 400, or 4,000 microcoulombs. Is that right? 600 divided by 3 is 200. 200 times 200, 4,000. Or is it 40,000? So another 0. Okay. That enough zeros? All right. So then I apply my 40,000 to each of these. That's my microcoulombs. They must have the same charge because they're in series. And now your job is to work backwards and find out the individual voltage. That's what I need to have here. So voltage equals charge divided by capacitance. So I'm thinking 400 volts and 200 volts. Now, there's a point to this, and I'm trying to get there. I'm meeting some resistance as you guys are having difficulty remembering capacitors. But this isn't so terrible, right? This isn't the hard stuff like shoving a dielectric in there, pulling the plates apart, or finding an electric field inside, right? This is just the simplification stuff. 600 volts with 300 ohms was what, 2 amps? So I have 2 amps here and 2 amps here. That's got to be 200 volts and 400 volts. Now, all of this was an attempt to show you something. I'm afraid it got lost in the execution of what I felt was going to be easy. So if you're going to pay attention to anything today and be awake for it, then this might be what to look at. Do you notice that the smaller capacitor got way more of the voltage, but the larger resistor got way more of the voltage? There's still proportionalities. One's directly proportional. The resistance is directly proportional to how much voltage you will get. But in the capacitor, it's inversely proportional. Resistors, it's based on a percentage. The percentage of the resistance to the total resistance is how much voltage you'll get. Right, the total resistance was 300 ohms. So the 100 ohm resistor got 1/3 of the voltage, while the 200 ohm resistor, which was 2/3 of the resistance, got 2/3 of the voltage. Right, direct proportion there. But with the capacitor, it's inverse. So keep in mind, when we're splitting out voltages, they operate differently. But they have similarities. The current and charge behaves the same. All right, well, I wanted you to see that. I'm afraid to show you this, but I'm going to have to. We've been working with circuits that allow for stepwise reduction. But there are a lot of circuits in the world. Our little simple circuits really are not so terrible, but they don't really do very much. I want to show you this circuit. What kind of circuit is this? Can you, in fact, here, I'll do more than this. I'll give you some numbers, and I'll make them easy numbers. Let's see if you can reduce it. So let's go with 3 ohms, 6 ohms, 4 ohms, 12 ohms, 2 ohms. Can you reduce this down to its equivalent resistance?